What is going on, everybody? It's Mr. Gust, and I'm back in the physics conference room. Today, we're talking about kind of the introduction to electromagnetism. We're talking about the right-hand rule. This is the basic convention we have that helps us understand the electromagnetic force between a magnetic field and a charge. And the first thing you have to understand is that a charge and a magnetic field that produce a force between them need to come from two different objects. So what I mean by that is I have a charge. If I have a point charge or a charge moving that moves along and it enters a magnetic field from something else, I need two different objects. If those two things interact, the interaction between the charge and the magnetic field, the electromagnetism, will result in a force. And we call that force an electromagnetic force. It's the interaction of those two things that cause a force. And today we're talking about the basics of the right-hand rule, and we're only talking about charges as they move through magnetic fields. So why do we call it the right-hand rule? Well, I've got a right hand, and my right hand actually shows three vectors that are all perpendicular to each other if I hold it palm up. So if I have my palm up, I actually have got three different parts of my hand that indicate three different perpendicular vectors. The first one is my thumb. My thumb is perpendicular to my fingers. My fingers are the second part of my hand that I can use. And the third part is tricky to see, but the palm of my hand points outwards. The palm of my hand is also part of this right-hand rule. So I've got thumb, I've got fingers, those are 90 degrees, and then coming straight out into the camera at you is my palm. Let's talk about what those things mean in terms of the interaction between a charge, an electro, and a magnetic field, the magnet, to produce an electromagnetic force. Let's talk real quick. I got over here the right-hand rule. The right-hand rule convention, at least the way I use it. Some people will say the right-hand rule is not an open palm. They'll say it's your finger, your thumb, and like your middle finger kind of pointed in this like right-hand rule type thing. You might see this in a textbook. That's not the way I do it. It's not the way I was taught it. It's not the way I learned it. I prefer to do it this way, and I will explain exactly why I choose this way. So the right-hand rule. The thumb is our current. It's not our charge, it's our current. And the reason why we say it's our current is because current is the direction of positive charge flow. My thumb always points in the direction a positive charge would move in. So if it's a negative charge, if I'm talking about how an electron moves, my thumb actually doesn't point in that direction. I would need to flip my thumb around or use my left hand. It depends on what you want to do. I'll talk about that later. But the thumb is the direction of the current on the right hand. The fingers represent the B field. Usually I have one charge, or at least one line of charge. I'm talking about a wire, but in this case, one charge, one thumb. I have many fingers, and a B field has many field lines. These fingers look like field lines. So I've got a charge, and I've got a field. Now, these field lines, when they interact with this moving charge, produce a force. Well, on my hand, the thing that produces force, if I want to go push on something, I use the palm of my hands. The palm is force. I've got charge, I've got B field, and I've got force. My open hand is the right hand, and it will tell me the direction a charge experiences a force in when it enters a magnetic field. Let's do an example problem. On the board here, I have got a positive charge. I don't care if it's a proton, just a positive charge moving. It moves through a magnetic field. My question is, in which direction does it experience an electromagnetic force? Let's use our right hand. So in this case, I want to point my thumb the direction this positive charge is moving in. It is moving to the right. So I will point my thumb in that direction. Now, I also want to point my fingers in the same direction as the B field because the fingers are my B fields. This is getting kind of tricky. I want to make sure my thumb points to the right, and my fingers are pointed up right now. I need to get my thumb to stay to the right in the same direction, and my fingers to point down. When my fingers are pointing down and my thumb is to the right, my palm is pressing into the board. So I would say the force this object would experience would be into the board. And we have a unique way to show that vector, right? Right and left vectors are easy, right? Right/left vectors are like this. Up/down vectors are like this. But into and out of the board, those are weird vectors. So we have to come up with a new system. Into the board, or into the page, we show it as a X or an X, okay? Sometimes it's a circle with an X, like the X-Men logo. Sometimes it's just X. The way I was taught is like if you're going to be laying in the page, if you're like sleeping on the page, you're into the page. X is like a cartoon, like your eyes are like X'd out, like boom, you're into the page, you're dead, like you're out. Like that's how I was taught. Right? And then out of the page, that vector looks like the tips of fingers coming at you. If you see my fingertips coming right at you, it looks like little dots. So out of the page is like eyeballs looking at you. So I have a little dot right there. So it's a circle with a dot in the middle because it's coming out at you. So if I wanted to draw this vector, I got my finger going to the right, my B field down, my palm is into the page. Because it's into the board, I would say my F is, or my force, would be X's. It would experience an into the page force. Let's try another example. I have got now a positive charge. Here's example number 1. Example number 2. I have got a charge, a positive charge, the direction of current, flowing to the right, and I have this time a magnetic field that has dots. We said dots is out of the page. I need to get my fingers to point out of the page and my thumb to point to the right. So thumb to the right, same direction as charge. I need my fingers to point out at me. So I'm gonna go like this. Fingers out at you, so you can see my fingertips. Current or charge is moving to the right. I guess now it's moving to my left. Actually, now it's my left. So moving to the left, fingers out, my palm is pushing which way? My palm pushes down. Palm is force. That means the force is directed down. Or I would say force is downward. This charge, if this charge goes through this B field, it would experience a downward force and it would shift and accelerate downward as it went through that magnetic field. Let's try one more example with this right-hand rule for a charge. This time, I have got a negative charge moving up, and I've got a B field moving to the right this time. It's moving to the right. Did I say left over here? I guess it is moving to my left if I face this way. And when I face this way, it's right. Huh, it's so weird. It's so bizarre. It's still the same. Here we go. I told you earlier, my thumb is the direction of the current, not the charge. We've described current all year long as the direction of a positive charge. There are two ways to think about this, and I will explain both. If my thumb is if my thumb is current, and this is a negative charge, well, the current flows opposite the direction of the negative charge. So instead of taking my right hand and pointing it up the page, I need to take my thumb and point it down the page because that is the direction that my current would flow in. It's the opposite of the negative charge. So I would say downward is the direction of current. The B field, my fingers need to point in the same direction as the arrows. And you see my palm is pointing right out at you into the camera. So my palm is out of the page in this case. The force would be out of the page. And we would say it looks just like an eyeball looking at you. We would say there it is, boom. Now, that's one way. The other way I have heard this spoken about, and I personally think it works best for me. You do what works best for you. When I see a negative charge, a positive charge is my right hand. A negative charge is not my right hand, it is my left hand. So when I see a negative charge, I simply don't use the right hand because the right hand is saved for current and positive charges. I use the left hand for negative charges, okay? So here's what I do. I go ahead and say on my left hand, because my right hand is positive charges, my left hand is negative charges. I go ahead and I point my thumb in the direction of the negative charge. My fingers point the direction of the B field, and what do you know? My force is still out of the page, even though I'm using my left hand, not my right hand. I still get the exact same thing. Left hand in the direction of negative charges, B field, force out, or right hand, opposite electrons. Either way I do it, I get a force out of the page. Both are acceptable. It depends on what you're comfortable with. I'm a left hand negative guy, right hand positive guy. It is totally up to you. This is the right hand rule for charges. For charges, this is our right hand rule. If you got questions, drop in the comments, send me an email, ask me in class. Till next time, see ya.